Hello everyone, my name is Enes. My friend Burak and I will present you our project on building assistant rank hit candidates in drug discovery. The project is supervised by Arzucan Özgür and co-supervised by Rıza Özçelik. During the presentation, we will be covering the following topics. First, I will present you the first four parts. Then Burak will present the results, conclusion, future work, and references sections. Let's start with the problem statement. Our project aims to develop a more efficient and accurate method of virtual screening for drug discovery. Virtual screening simulates the binding of compounds to a target protein to identify potential drug candidates. Current methods are often inefficient and yield low hit rates, which is a problem in the early stages of drug development. Traditional methods of representing chemical compounds like smiles capture only a limited complexity of the compounds, leading to inaccurate ligand ranking and misidentification of potential drug candidates. We will now move on to the motivation part. Our project aimed to improve efficiency and accuracy of virtual screening in drug discovery by using advanced vectorization techniques to rank ligands in a validation set based on similarity to a training set. Our research questions were how to improve accuracy with advanced vectorization techniques, what is the best vectorization method for virtual screening, and how to improve ligand ranking for accurate drug candidate identification. We will be diving deeper into these topics throughout our presentation. Let's now continue with the dataset explanation. We used the LIT-PCBA dataset as a benchmark dataset in our project, which includes 15 targets, around 8,000 active compounds, and around 410,000 inactive compounds represented in SMILES, activity status, and target protein information. The data is preprocessed by tokenizing SMILES, vectorizing the data, and splitting the dataset into training and validation sets. Although the LIT-PCBA dataset is of high quality, it has limitations in terms of size and diversity of compounds and targets, which may affect the generalizability of our results. We will now move on to the methodology part. Our methodology for this project includes using advanced vectorization techniques such as tokenization methods like LINGO and Byte encoding, fingerprint-based vectorization, and well-established similarity measures like Euclidean, Cosine, Tanimoto, and Dice to improve the accuracy of ligand ranking process. We also employed machine learning techniques such as TF-IDF and vector space models to analyze and process the data. We recognize that further optimization is possible, such as incorporating 3D structure data and using larger and more diverse datasets in future work. So now Burak will continue with the results of our project.
Among the chemical rankings using TF-IDF vectorization methods, choosing LINGO instead of byte pair encoding as tokenization method performed better. Fingerprint-based chemical rankings performed better than the others, and all of them performed better than random rankings. And among fingerprint-based chemical rankings, Cosine and Euclidean similarity-based ones performed better. We have two metrics of comparison, top K and enrichment factor metrics. These are frequently used in virtual screening studies. In the left, you can see top K scores, and right, you can see enrichment factors. To make enrichment factor plots more readable, we use moving averages. By definition, enrichment factor converges to 1 when x is getting near to 100%, and top K also converges to ratio of active ligands in the database. You can easily see from the plots yellow and pink, which are fingerprint-based methods using Euclidean and cosine similarity, are performing best, and the lowest performing ones are random rankings. In this page, there are two graphs showing success of the chemical rankings we tried. The metric is enrichment factor here, and x is 1.6%. Why we picked such a small value? There are two reasons. One is the convergence, we talked it in the previous page, and the other is there are lots of ligands and it's costly to try all of them in drug discovery. One of the aims of the chemical ranking is finding correct ligands by trying a small percentage at the top of the ranking. Therefore, a small percentage like 1.6% is chosen. The graph at the left shows the enrichment factor metrics of the rankings. We can easily see the most successful ones are fingerprint-based ones and LINGO TF-IDF based ones. The graph at the right shows how much better the proposed rankings performed, better compared to average of 3 random rankings. It's easy to see that all of them performed better than random rankings. The best performing one is fingerprint Euclidean ranking, which is 7.5 times more effective than average of random rankings, while even the worst performing ranking, the byte pair encoding TF-IDF based rankings, performs 1.5 times more effective than average of random rankings. And here's a conclusion of results. We talked about them. It's a 2-semester long project, and in the next semester we are trying to improve it. What can be improved? First, natural language processing and deep learning based ranking methods can be developed, and we may compare their efficiencies. The other is we may use larger databases, and the other is there are very popular two approaches in drug discovery: the ligand-based approach and structure-based ones. We used ligand-based ones. We may try to use structure-based ones in the next semester. Here are some of the works we referred during the project. Here there's only most important ones. To see all of them, you can check the report. Thanks for listening.